Hello everyone. In this video, we'll be talking about equations of first order and higher degree. So just as the name suggests, this refers to differential equations where the derivative of y with respect to x is in a higher degree. So in order to understand what the degree of a differential equation means, you can refer to the video on Picard's iterative method, where the order and degree of differential equations have been explained. In order to solve these types of differential equations, we will represent the derivative of y with respect to x, that is dy dx, by an arbitrary letter, say p, and I'll be using p for the most parts of this video. So you can use any other letter of your choice as long as you are not using the dependent and independent variable. So the differential equations will be of the form a function in x, y, and p to be equal to 0. So whenever you have this kind of differential equations, you know you're referring to equations of first order and higher degree. And they come in four cases. So the first case is the equations solvable for p, that is solvable for dy dx. So the second case refers to the equations solvable for y. The third case refers to the equations that are solvable for x. And the fourth case is what we call the Clairaut's equation. So whenever you have differential equations of first order and higher degree, they usually come in either of these four cases. So in this video, we'll be starting out with the first two cases. Then in our next video, we're going to take a look at cases 3 and 4 respectively. So in order to consider case 1, which is the equations that are solvable for p, we have equations solvable for p. So we're going to take a look at a question in order to discuss the method of solution. The question says we should solve the differential equation x squared, which is equal to 1 plus dy dx squared. So this is an example of a differential equation of first order and higher degree. First order in the sense that the highest derivative there is of order 1, that is dy dx. We are not looking for the second derivative, we are not looking for the third derivative, and so on. So we are looking for the first derivative, and that's why it's a differential equation of first order. Then the higher degrees, because this differential has been squared, so it's no longer the regular way we've been doing it, where we have the derivative just raised to the power of 1, and that's why we wrote dy dx for most parts of the questions that we have been solving. So we are required to solve this differential equation x squared is equal to 1 plus dy dx all squared, and we are going to discuss the method of solution of differential equations of this case. So in order to do the solution, let's take a look at the solution now. Now, in order to solve these kind of differential equations, the first thing we are required to do is to set dy dx to an arbitrary letter. And remember that this letter shouldn't be y or x because they are the dependent and independent variables respectively. So in this case, like I said, I'm going to mostly be representing it as p. So the next thing in this kind of differential equation is to make p the subject of the formula. Remember, it's a differential equation solvable for p. So I'm going to make p the subject of the formula. Then when we are done with this, we'll set p back to dy dx. After which we integrate both sides. In order to get the solution for y. So now it's important to also note that this method works for differential equations that involves dy dx and functions in x only. So when you have a first order differential equations that only has dy dx and a function in x only, then you should apply this method, which is the equation solvable for p, because in that case p can be easily made the subject of the formula. So now let's go ahead to do this. So we have x squared is equal to 1 plus dy dx all squared. So by setting dy dx to be p, we have x squared is equal to 1 plus p squared. Then we can simplify this by saying p squared is equal to x squared minus 1. So we've made p squared the subject of the formula here. But we need p. So to do this, we would find the square root of both sides. So we have p squared raised to the power of 1 over 2 will be equal to plus or minus square root of x squared minus 1. I should divide this place into 2. So which means p now becomes plus or minus square root of x squared minus 1. Now we should recall that p is equal to dy dx. So we have dy dx is equal to plus or minus square root of x squared minus 1. Our dy now becomes plus or minus square root of x squared minus 1 dx. So we can go ahead to integrate both sides now. On integrating both sides, we have that the integral of dy is equal to plus or minus the integral of square root of x squared minus 1 with respect to x. So we have that y is equal to plus or minus the integral of square root of x squared minus 1 dx plus a constant, which is a constant of integration. So on integration, we have that our y now becomes plus or minus x multiplied by the square root of x squared minus 1 divided by 2, then plus or minus 1 over 2 ln x plus square root of x squared minus 1 plus c, and this becomes our solution to the differential equation. Now let's take a look at the second case study, which is the equations solvable for y. So to start with this discussion, we're going to take a look at the solution steps. So the first thing to do when you have differential equations of this form is to differentiate the given differential equation with respect to x. With respect to x. So after differentiating it, you eliminate p, which is dy dx, from the given equation. And also the equation that we obtained after differentiating with respect to x. So say the equation obtained from the step above. And the last thing is that the eliminant is a required solution of the differential equation. So we're going to take a look at the question to show how this method works. So here goes the question. Question says that we should solve the equation y is equal to x minus a dy dx minus dy dx squared. So remember, the first step is to set dy dx to be equal to p. So on doing that, we have our equation to be x minus a multiplied by p minus p squared. So we can see that we can't use the method we described for equation solvable for p because we have functions in x, y, and p. To use the equation solvable for p, it has to involve just p and function in x. So now we'll differentiate with respect to x. On doing that, we have dy dx is equal to p plus x minus a dp dx using product rule minus 2p dp dx. So we know that dy dx is equal to p. So we can write the equation to be equal to p is equal to p plus x minus a dp dx minus 2p dp dx. So we can now eliminate p from the new equation that we've gotten. So we now have x minus a dp dx minus 2p dp dx is equal to 0. We can then factorize the pdx out, and we have the pdx into brackets x minus a minus 2p to be equal to 0. So we now have that the pdx is equal to 0 on dividing both sides by x minus a minus 2p. So we have dp to be equal to 0 dx, and we can go ahead to integrate both sides. So we have the integral of dp is equal to integral of 0 with respect to x. So on integrating both sides, we now have that p is equal to c, which is a constant. You can then use this to eliminate p from the original differential equation, because we have y is equal to x minus a into bracket p minus p squared. So now we can set p to be equal to c, and we have that y is equal to x minus a into bracket c minus c squared. And this is going to give us the solution of the differential equation. Thank you very much for watching this video, and we're going to discuss about the remaining two case studies in the next videos.